Hi everyone, today I am going to present my digital communication lab experiment, which is experiment 4, Uniform Quantization and PCM. My name is Krishnandupal from third year EC department. In this experiment, I have implemented Uniform Quantization and PCM encoding using Python. The main aim of this experiment is to implement Uniform Quantization and PCM encoding for sinusoidal signal. We first normalize the signal, then quantize it using different numbers of bits. After quantization, we calculate the quantization error, MAC, SQNR. Finally, we compare, we measure SQNR and compare with theoretical values. Now, going to the theory, we can see here in an n-bit PCM system, the total number of quantization level is L is equals to 2 to the power n. For example, if we use 3 bit, then we get 8 levels. Since our signal is normalized between -1 to +1, between -1 to +1, the quantization step is 2 by L. Now, the mean square error, now the mean square error is the average square conjugation error. And the SQNR is 10 log 10 px upon pe. And the theoretical SQNR for the full scale sinusoidal signal is approximately SQNR is equals to 6.02 n plus 1.76 dB. Quantization error is the difference between the original signals and the quantized signal. So E is equals to x minus x cube, and which represent the average squared quantization error. Now, here is the complete Python program. In this slide, we see the complete Python program we implemented before. After after explaining this part, uh, we generate a sinusoidal signal, a normalize it between -1 to +1. Then I take difference bit resolution 2, 3, 4, 5, 6, and 8 bits. For n, each value of n, the program calculates the number of labels, quantize and samples, generate the quantize indicates and corresponding binary PCM word. Finally, it calculates MAC and SQNR and perform the required validation. Now, if I see the code in Google Colab, this is the total code, and we get this type of waveform. This is the quantized waveform for 3 bit. This is amplitude versus time graph, and the original signal is blue, and the quantized signal is orange signal. Here the staircase characteristics of uniform quantizer, and after that the quantization error uniform for 3 bit. This is the 3 bit. This is the graph for 3 bit, and I take 3 bit for every perform. This is the histogram of the quantization error, and the SQNR versus numbers of bits. This is the number of bits, and this is the SQNR. If we plot this, we get this type of linear equation. And after this portion, this is slightly uh, go far from each other, and the orange is the theoretical SQNR, and the um, blue is measured SQNR. And this is the final result, where the measured SQNR is this and the theoretical SQNR is this. This is a quite difference between these two values. For the measured for bits 2, it's 12.8058, and the theoretical value is 13.8. What the program does. Actually, what the program does, the program performs the complete quantization process. First, the sinusoidal signal is normalized. Then the signal is divided into uniform quantization level. Each sample is assigned a quantizer index. Then the index is convert into a n-bit binary PCM word. After that, we calculate the quantized error, MAC, and SQNR. For example, with 3 bits, the number of levels is rate. So the indicate range from 0 to 7, and each PCM word contains actually 3 bits. This is the expected SQNR from these theoretical, sorry, this is the expected SQNR from this theoretical equation. We get this type of values for 2, 3, 4, 5, 6, and 8 bits. And this is the result. This is the actual output for measured SQNR for 4, 8, 2, 3, 4, 6, 8. It is 12.8085, 19.0646, 46, 25.2264, 36.3377, 48.7230. The theoretical SQNR for the full-scale sinusoidal signal is approximately 6.02 n plus 1.76 decibel. This equation. This means that when we increase the number of bits by 1, the SQNR increased by approximately 3 decibel. For 6 dB, sorry, 6 dB. For example, for 2 bits, the theoretical SQNR is approximately 13.8 dB, while for 8 bits, it is approximately 49.92 dB. So, higher bit resolution gives better signal quality. And this is the output waveform we see before. This is output result. And the observation, from this observation, we can see the increasing the number of bits increase the number of quantization level. Therefore, the step size becomes smaller and the quantized waveform becomes a better approximation for original waveform. And the conclusion for this conclusion part, we conclude uniform quantization and PCM encoding were successfully implemented using Python code, and we see this there is a little difference between theoretical and measured SQNR value. That's all from my side. Thank you.